Oh, this sounds ultra cool here. Okay, got it here. Okay, so what I'd like to do with you, share tonight, a new triage technique that we've just published, the neutrophil to lymphocyte ratio, and a triage tool for criticality accidents. And see here. As Carissa noted, my PhD is in physics and a medical degree from George Washington, and I have an MPH from Tulane. You know, I really, to be honest with you, I'm still a physicist here. I spent a long time in the DC area. Of course, I went to GW. We lived in Southern Maryland, in Waldorf. Both my sons were born in Maryland, so they consider themselves Marylanders. And I spent almost 4 years at NIH. So, you know, I still feel very linked to that area. So just to start off, kind of get us on the same wavelength, what is a criticality event? Now, from a health physics viewpoint or nuclear engineering viewpoint, it's pretty interesting. It's a accidental uncontrolled nuclear fission chain reaction. Sometimes it's called a critical power excursion. From a personnel point of view, generally people are around the thing. So there's an unintended critical mass and a power excursion, and these criticality accidents historically have involved potentially fatal radiation doses. Now, from a medical point of view, which is where I'm coming tonight, if we're triaging a number of patients, we have multiple patients to triage with exposure to a mixed gamma and neutron field. From a medical point of view, it's not so important for me in the triage situation to know exactly what happened. It's just that we have patients with a mixed gamma field. So also, in my opinion, the criticality accident is the best surrogate for the medical management of patients from explosion of improvised nuclear and IND. So typically in the health physics realm, we talk about for a mixed field, we talk about gray equivalent, which is the gamma dose plus an RBE times the neutron dose, the relative biological effectiveness factor. Historically, for criticality, the RBE has been about 2. Some people are thinking it's more like 3 now, but it's close. So I would point out here a really, really good reference from Los Alamos, a review of criticality accidents. It's free. It's in a PDF form. It's on the internet. And it was written by both U.S. and former Soviet Union scientists. So it has a description of accidents both in the U.S. and in the former Soviet Union. We don't really have much in the way of criticality accidents in China or in other countries. Another good reference that I have used a lot, you probably know some of this, is a William Robert Johnson's database of radiological incidents. This has a really good summary of health physics in all of these accidents. I've gotten the medical information from other places, in particular our REACTS accident registry, the REACTS accident registry. For those of you who don't know REACTS, the Radiation Emergency Assistance Center and Training Site, or REACTS, is in Oak Ridge, Tennessee. So I'm coming to you from East Tennessee right now, and it is the Department of Energy's asset for the medical management of radiation accidents. And so we basically do a lot of triage phone medicine. You know, people come in, we ask them what's happening. And so we have some cases going on right this minute. And so not criticality, but what things that we see a lot of, we see internal deposition. We had a case out of New York recently on internal deposition of americium-241. We see a local injury. Someone gets close to a source or to a beam. We had a case in Michigan that we're dealing with a medical physicist, actually, who accidentally got his hand into an accelerator beam. So we're dealing with a variety of things. Okay, let's see now. So let me point you to a paper that we published in Health Physics just last year. Neutrophil to lymphocyte ratio is a triage tool to criticality accidents, with my colleague Carol Iddens, who is director of REACTS. Now, I chose criticality accidents because I think it's important for a weapons event, but also, you know, this technique works for gamma accidents also. And so it really works for any kind of radiation incident. I had a little bit better compilation of data for the criticality, so that's why I published it this way, but we equally could have included gamma. So you can take a look at this. This is volume 4 of last year. So we're going to triage. Why do we need this? So in criticality triage after a radiation event, as medical providers and health physicists, it's necessary to decide whether the patient has a clinically significant dose. And BARDA has defined that as 2 gray. So we want to, for 200 rad, so we want to decide, given a patient that comes to us, does this patient have a clinically significant dose? So if the answer is yes, then it would require referral to more definitive health physics evaluation. So it's a binary decision, yes or no. And the reason we chose the neutrophil lymphocyte ratio as a decision parameter, it's simple to obtain in field operations. And so our question is then, we're going to determine a threshold value for the neutrophil lymphocyte ratio, NLR, such that if the neutrophil lymphocyte ratio is over this threshold, patient to then be referred for more definitive health physics and medical testing. And in medicine, we have this all the time as to whether a test is abnormal or not. And the typical statistic in the medicine realm is use receiver operating characteristics and analysis, and we'll use that to determine our threshold here. So we're, I think, some of the first to use this in the health physics field. My colleague Bill Blakely at AFRI has also used it, and he and I have been on a learning curve together for the ROC analysis. So what do these cells look like? You know, we're going to analyze neutrophil to lymphocyte ratio. So here we have neutrophils. They're multilobulated cells. They help fight bacterial infections. They have multiple granules in the cytoplasm. The lymphocyte is agranular. It has a smooth, relatively smooth cytoplasm, and it has a big nucleus, as you see there. It covers almost the whole cell. And so the lymphocytes are the most sensitive to radiation of all of our cells. So in the neutrophil lymphocyte ratio, it's a marker, a nonspecific marker of systemic inflammation, okay? And it's elevated in many different inflammatory states. So I was actually somewhat shocked when I did a literature search on this. There are over 60 papers in the literature indicating that neutrophil lymphocyte ratio is a marker of chronic systemic inflammation. Various cancer states, almost all cancers, chronic kidney disease, cardiovascular pulmonary disease, immunologic disease, infectious disease, including COVID. A Chinese group published on the neutrophil lymphocyte ratio. If it's significantly elevated, it bodes bad for pulmonary aspects of COVID. And we've done radiation accidents, the criticality and gamma. And I would also note, I didn't get on this list, that I'm looking at the radium dial painters, these young women that, you know, tipped their brush as they were painting watch dials and therefore ingested radium-226 and radium-228. And so we're looking at that as part of the million-person study. So I found a review paper. So I had looked at all of these studies, and everybody says that the neutrophil lymphocyte ratio is a marker of inflammation. Okay, well, why is that? So I began searching, and a new paper just came out in the International Journal of Molecular Sciences just recently, I think 2022, saying that the neutrophil lymphocyte ratio is a marker of the relationships between the immune system and disease. And in particular, I excerpted some sentences here. It's the ratio, of course, between a neutrophil and lymphocyte counts and a peripheral blood count, a complete blood count. But it's a biomarker which conjugates 2 faces of the immune system: the innate immune response, which is mainly due to neutrophils, our innate response, and the adaptive immune response that's mostly supported by lymphocytes. And so when the neutrophil lymphocyte ratio goes up, this is characterized by an increase in neutrophils and a decrease in lymphocytes typically. So I want to point out my mentor and friend, and I'm sure for many of you also, Dr. Neil Wald, who passed away a few years ago. He, as far as I can tell, was the first, he and his student, Dr. Zhang, were the first to note that the neutrophil lymphocyte ratio was a good prognostic indicator. This was in the annual health physics meeting in McLean some years ago. Now, the neutrophil lymphocyte ratio, I think, could very easily be a value that we could get in the field. We have portable hematology units, and here are some pictures of these. So we can get a complete blood count. In medicine, we call it a CBC, and we can get a listing of the different components, the fractions. That's called a differential. So we can get a CBC and differential in the field in a triage situation with just a small amount of blood. All right, let's look at this. So here is a complete blood count. We call it a CBC with differential, CBC and diff. So we have the WBC, the white count, the red blood count, hemoglobin, hematocrit, and then the cellular indices, MCV, the mean corpuscular volume, the mean red cell volume, the mean corpuscular hemoglobin, average hemoglobin in the red cell, and the mean corpuscular hemoglobin concentration. Also, a statistic, the RDW, which shows the width of the distribution width of these. We have platelets, and then it gives you the differential, the percentage of neutrophils, the percentage of lymphocytes, percentage of monocytes, eosinophils, basophils, etc. So the absolute neutrophil count would be the percentage times the absolute. So we have here, this is an automated count, so it'd be 47% were neutrophils, 46% lymphocytes. Generally, this is more 1-to-1, but generally it's like 2-to-1, neutrophils to lymphocytes. So looking at Dr. Wald's slides going back a few years, here is his very nice picture of the acute radiation syndrome. Normally in our peripheral blood system, we lose blood cells that are recycled, and those are replaced from our bone marrow, the cell factor in his slide here. So we have a steady state. What's lost is typically replaced. However, in acute radiation syndrome, we're still losing cells, but we have an increase. We're losing cells, but we have a decrease, or a relative or absolute decrease from the bone marrow. So the bottom line is you have a loss of both white blood cells and platelets. So here is a graph that you see in some of the textbooks in acute radiation syndrome. Say for a patient that has 3 gray or so, if you look at the little mustard colored slide, the lymphocytes go down quickly after say 3 gray whole body dose. And we've published some stuff in the material in the past on the on lymphocyte kinetics. So the faster lymphocytes go down, typically the higher the dose. The neutrophils go up initially. It's probably a stress response, a demarginization. And then they go down and bottom out maybe 25 or 30 days after the event. And the same for platelets. They have a decrease maybe 30 days after the event. So the bottom line is, in the acute phase of relatively high level dose, say 3 gray or so, neutrophils increase, lymphocytes decrease, and so that neutrophil lymphocyte ratio goes up. And so in the right-hand corner, I've just enlarged this a little bit. You can see the lymphocytes go down exponentially, and the neutrophils go up, so that ratio goes up. So looking at the neutrophil lymphocyte ratio, we have put together a criticality accident data set using historic complete blood counts from 12 criticality accidents with 33 patients. This is from the accident registry at the Radiation Emergency Assistance Center and Training Site. In addition, I've put together a cohort of 125 normal controls. So in the control set, the neutrophil lymphocyte ratio is found to be 2.1 plus or minus 0.06. and consistent with the Gaussian distribution, but barely consistent. It's, you know, just right on the edge, actually. And I see my colleague, Dr. Blakely, has joined. He has done very similar work with primates, and we fortunately find the same control neutrophil lymphocyte ratio, which is good. We actually agree on it. So here are the criticality cases that we have looked at. We had data for, and a couple of these we'll talk about. The Y12 liquid criticality in June of 1958. 3 at Los Alamos in 1945 and 48. In particular, Lanol 2 and Lanol 3. Lanol 2, and both of these involved the plutonium sphere that I'm sure you've seen. 2 hemispheres, and the first one, there was a solid criticality event from stacking tungsten carbide blocks and actually getting more of a reflector, and it went critical. A patient died of acute radiation syndrome, the hematopoietic portion, 28 days after the event. Lanol 3 was a similar death with that same plutonium sphere, but here in a demo, the top hemisphere was held by a screwdriver, and it slipped off the screwdriver. That patient died after approximately 9 days with the GI portion of acute radiation syndrome. So we've looked also Lanol in 1958, Vinca, Mole, Wood River Junction in 1964, Tokamura in 1999. So we'll talk about Y12 and Tokamura. And we also have data from Savarov and Hanford and Argonne. So these are the cases that I had data for. There are actually a lot more very nice cases that I didn't have hematological data for. So let's look at the Y12 criticality accident. This is kind of interesting. It was a liquid criticality accident. So these slides are from the Los Alamos review of criticality accidents. So basically what was happening, there was a leak in a container that contained 93% uranium-235. It was discovered but not logged. The following day, other tanks were being drained into a 55-gallon drum. And so basically you had, and like in all of these criticality accidents, you have a critical mass that's formed either from liquids or from a solid situation. So the operator nearest the drum noted yellow-brown fumes rising from the drum's content. He retreated before seeing a blue flash as the criticality excursion. And as you tend to have in liquid events, it oscillated for some minutes. So 8 people received significant doses. Now, I've had the opportunity to deal medically with 4 of these 8 individuals. They've all been very nice. And I still see one of them. But the one I see now tells me that when this happened, he saw a blue light go across the ceiling. And so, as you know, this is Cherenkov radiation. And so here's a picture of Cherenkov radiation in a reactor pool, actually. But Cherenkov radiation, as you know, is when you have charged particles, typically electrons, that are moving faster than the speed of light in that medium. So like in a water medium, they're moving faster than the speed of light is. So that blue light, which he saw moving across the ceiling, was Cherenkov radiation. So here's some pictures from the Knoxville News Sentinel at the time. The workers were all told to put their badges in a basket, and they all gathered near one of the guard towers here in Oak Ridge. So this is 1958. Now here is the film badge that they carried, and it's just one that I used when I first started as a summer student at ORNL in 1966. So the film badge had neutron components for neutron dosimetry. But I'm told, and I've actually never seen this in a textbook, but I'm told that they didn't have their badges on. Most of them didn't wear their badges. So I'm just looking here, still recruiting. So this is what they would have had if they'd worn the badges. But here is a very good reconstruction, a reference from Sam Hurst and Rufus Ritchie on the dosimetric aspects of the neutron and gamma ray accident. So you can take a look at that if you care to. So here are the patients that I have dealt with. I've dealt with 4 of these 8. A patient A had 365 gray, or going with gray equivalent again. You remember the gray equivalent's the gamma dose plus an RBE times the neutron dose. In 1958, the RBE was considered to be 2. And so patient A got 4.61 gray equivalent, and it goes on down. Patient B, 4.28, patient C, 4.13, patient D and E, etc. And then there were 3 patients with relatively lower doses, and patient H is still the one that I see, and he only got 0.23 gray or 0.29 gray equivalents. He is funny. He's in his mid-80s, and he calls me up on the phone. We talk. He's got a very nice Porsche convertible he's trying to sell me, but anyway, he's a very nice guy. I see him on a yearly basis for physical exam and that sort of thing. So here is what the white blood count looked like when it was reported in 1958 by Dr. Brewser, who was head of the medical division at Oran's Oak Ridge Institute of Radiological Studies. On the y-axis, we have the white blood count in thousands, and the x-axis days post-exposure. So you can see that for these individuals, they bottomed out their white count, which is predominantly neutrophils. They bottomed out their white count in like 28, 30 days. So what's the neutrophil lymphocyte ratio for these? I have access to their medical files and their hematology data, so we were able to calculate that. So looking at patient A, his RBE weighted dose is 4.61 gray equivalent. Neutrophil to lymphocyte ratio was 4.8. So remember, control was 2.1. So patient A, we would have considered suspicious on our test. Patient B, 5.7, yes. We're going to find when we talk about the ROC analysis that if the neutrophil to lymphocyte ratio is over about 3.3 or so, we would be suspicious and we'd refer the patient. So patient A is 4.8, patient B 5.7, patient C 5.8. Now patient D had over 4 gray, but he was still within controls. So not everybody responds on these things. This is part of the problem. I mean, you have true positives and you have false positives, and you have true negatives and you have false negatives. So he'd be a false negative here. Patient E had 2.98, so he would be hit above our triage mark, as did patients F and G would go above, even at 0.86, and patient H would not have. So this is what we had, and these were in the first 12 hours. And so this is what we want to do, is to look at this as a triage instrument. So I got the data wherever I could, but within the first 12 hours after the accident. Some people respond in 4 hours, within 4 hours, and some patients in this data set take 6 or 8 hours to respond. So how does this look as a function of time? Neutrophil lymphocyte ratio is a function of time. So suppose we have a weapons event. So you're going to have some people go to the reception centers immediately. Some people are going to straggle in a day or 2, 3 later. And so what we found in looking at our data set is for under about 15 days or so, about 2 weeks after the event, the neutrophil lymphocyte ratio is generally greater than controls. And surprisingly to us, for times under about 3 weeks or so, it's less than controls, just for the kinetics of the situation. So I decided to take a look at this from the atomic bomb survivors. And Alderson and Shields Warren from the Manhattan Project published a very nice book on the medical effects of the atomic bomb in Japan. So here's a picture of this. We have copies of it. And I would recommend you get a copy if you can. It's very well documented. So here we have a graph that we've taken from our paper, health physics paper. On the y-axis, we've got the neutrophil lymphocyte ratio and versus x-axis time in days. So above about 20 days or so, the circles here, this is patient B, 2.45 gray. The circles are above our control line, okay? And then after about 3 weeks, it dips below the control line, just from the kinetics of the disappearance. And so on here, we've plotted some data from Hiroshima and Nagasaki. Hiroshima is in the solid circles, and Nagasaki is in the triangles, dark triangles. After the atomic bombs at Hiroshima and Nagasaki, it took about 3 weeks, 2 to 3 weeks, for Japanese physicians to get into the city and set up response centers. So we really don't have good early data, but we do have late data after about 3 weeks. And you can see that the Hiroshima and Nagasaki data is under controls from about 20 to 40 days. And then it pretty much hits our control line. So it's reassuring that their data from 1945 hits our controls now. Now, in looking at the Y12 accident, we plotted it as a function of dose equivalent. And so there is some evidence that the neutrophil lymphocyte ratio is linear with dose. And so we have a reasonable linear fit here. R squared's about 0.55. It's not great, but it's reasonable. Okay, so that's Y12. Let's look at Tokamura and the criticality accident. This is the last criticality accident that we've had, September the 30th, 1999. And this is particularly interesting to me because I had come to REACS in 1994. I had spent from 79 really to most of 94 at NIH, either in medical school or residency or at NIH. And so I had just come back to REACS, and as the criticality event was happening, our Japanese colleagues were faxing in hematological data to us. So that was very nice that we were able to get the data in real time. So where did Tokamura occur? It's in the eastern part of Japan, up from Tokyo. Very nice set of reactors there, a scientific facility. I had actually been there before this happened. So Tokamura, here's a tourist brochure. It's synonymous with nuclear research in Japan. And the research laboratory at Tokamura was built in 1956. So here's the accident. We had 2 workers that were dissolving uranium oxide, 18.8% enriched, and pouring the oxide in with nitrate into a precipitation vessel. So we had 3 patients. Mr. O was standing on the floor holding a funnel. Mr. S was leaning over, pouring the solution into the funnel. The supervisor, Mr. Y, was in his office 5 meters or so away. So here's a picture of this. If you had to guess just from looking at it, I mean, which of these would you think would get the highest dose? Well, my opinion, Mr. O, because he's standing there, he's almost wrapped around the precipitation vessel. And Mr. S is getting a high dose also, but a really high dose to his feet because he's standing on the ladder. So Mr. O, you would think, would get a high dose to his head and thorax from just his position here. So here's actually the picture of the facility. The authorized procedure was to dissolve the uranium oxide into nitric acid and then bring out under 2.4 kilograms into the bottles. I'm told that they were hurrying. What they did was they poured 16.6 kilograms into a bucket and put that into the precipitation tank. So like all of these criticality accidents, either solid or liquid, you have over a critical mass, and then you have an excursion. This being a liquid system, it oscillates. So think about it. You have a liquid solution, over a critical mass, and then you have heat and energy in the liquid, and it then comes up on the side of the tank, and then it comes back down, gets critical again, and comes back up, goes subcritical, et cetera. So it oscillates. And this solution oscillated for about 18 hours or so until they were able to drain a cooling jacket. So here are some details here. It's happened at 10:35 a.m. local time on Thursday, September the 30th, 1999. Prompt criticality. All 3 of the men talk about a blue flash, the shrink off radiation. The gamma alarm sounded Mr. O and Mr. S left the room. Mr. Y, the supervisor, reported it by telephone. It's not clear whether he did that before or after he left. But the initial burst was about 7 times 10 to the 16th fissions, and then going to 3 times 10 to the 18th total because it oscillated for hours. Physical consequences, there were no explosion, but the release of gaseous fission products, krypton, xenon, and this thing pulsed for like 17 or 18 hours until they were able to drain a cooling jacket, which is serving as a partial reflector. So this was the end of September, and external gamma levels in the facility from fission products were still too high to permit entry by the end of October. So medical evaluation, the ambulance arrived at 10:46 very promptly and departed for National Meadow Hospital. And then eventually all three of these were flown to the National Institute of Radiological Sciences in Chiba. It's on the outskirts of Tokyo. We have dealt with our colleagues at NIRS. They've come to us, and so we have a collaboration. And then because of the seriousness, so NIRS is mostly or heavily a research hospital. And then Mr. O and Mr. S were, because of the seriousness of their injuries, they were transferred to the ICU at the University of Tokyo eventually. So here's Mr. O. We're going to find he had the highest dose. He had a loss of consciousness almost immediately. A transient incapacitation, questionably had a history of epilepsy, but anyway, incapacitation, loss of consciousness, severe vomiting immediately. So I haven't included that tonight, but you know that one of the prodromal symptoms is vomiting. So the higher the dose, typically the sooner you vomit. If you vomit within, say, 1 hour, you're talking probably 4 or 5 gray, possibly. But when you vomit within minutes, you're probably talking about a lethal dose. He had diarrhea, continued for 4 days with blood in his stool. He had erythema, redness and swelling edema of his face, arms, had pulmonary edema and pleural effusion, fluid in the lungs, and eventually went into kidney failure. So I'm going to show you some local injury, but I would just point out to this paper was on cutaneous injury. I want to point out some of the thresholds with cutaneous injury. This is from a paper that just came out, Journal of Radiological Protection, by a colleague, Carol Iddens, Andrea DiCarlo at NIH, Mark Irwin at REACS, Eduardo, formerly at the IAEA, now has moved to France. So this is kind of an interesting paper. So you have epilation at 3 gray to skin, definitive maybe by 7 gray at 10 gray to skin. Dry desquamation. Dry desquamation is damage to the basal layers of the skin. It's like a bad sunburn. Moist desquamation, blistering, 15 to 20 gray. Our French colleagues will say that anything over 25 gray, 20 to 25 gray is not going to heal up. And so what they will do is get a health physics evaluation of a local injury and then excise anything that they think is over 25 gray. We haven't quite done that, but our French colleagues have done it very successfully, actually. So anything over 25 gray is probably going to be so necrotic it's not going to heal. Our case that we're dealing with, we've just about to finish dealing with it in Michigan, it probably got 18 gray or so. So it was, and we weren't sure it would heal, but apparently it is healing. It's good. So here's Mr. O. Here's his skin. You have on his right arm, you have erythema, you have blistering. Here he is in the ICU. You can see that he's got an endotracheal tube in, he's got a Foley catheter. This is Dr. Akashi, who's formerly the head of NIRS, and he came and worked with us at REACS for some time in the mid-1990s. He is a hematologist and actually trained at UCLA. So here he is with Mr. O. You can see the swelling of the abdomen, erythema, burns to the right arm particularly. Remember, Mr. O was standing right up over this vessel and holding the funnel. So follow-up, he had severe skin damage over more than 50% of his body. was losing over 2 liters of fluid a day, had one episode of cardiac arrest in early December, but was resuscitated and died of massive organ failure on December the 21st, 1999, 82 days after the event. And, you know, our Japanese colleague, I mean, this is a remarkable event that they did to keep him alive this long. I've had people ask me, why did they resuscitate him? But, you know, when he had a cardiac arrest, because everybody thought he was going to die. And so when we had some of our Japanese physician colleagues come to REACTS, I asked them that question. And they said the family requested that he be resuscitated. So that's a good answer. And it worked, but he eventually died of multiple organ failure. Now, Mr. S had nausea and vomiting within an hour. So he has a less dose, no diarrhea, edema, erythema of his face, trunk, blistering formation. He dropped his lymphocyte counts early and had transient hypoxemia, you know, decreased oxygen in the blood, but he was a smoker, so it's hard to tell. Here's a picture of him, again, in the ICU. And you can see the erythema and redness on his face. His right hand's bandaged. Now here's a picture of his foot. And this is dry desquamation. And if you look at it carefully, you see the little punctate white dots. Dr. George Volz, you may remember, some of you may remember him, a physician at Los Alamos, told me one time that if you want to look for dry desquamation in a radiation injury, look in the creases of the feet or hands and that sort of thing. And so you can see the dry desquamation here, but particularly if you look at the creases in the foot and the toes here, you can see this. So this is at least 10 gray to his foot, and this is damage to the basal layers of the skin. Okay, let's move on here. So follow-up, he thought that he might do okay, but he ended up with an antibiotic-resistant pneumonia, Klebsiella, and went into pulmonary edema, was placed on a ventilator, went into kidney failure, had a mucositis, tissue shrinkage in his mouth where he couldn't eat or swallow, and again died of multiple organ failure 210 days post-exposure. So again, a very heroic effort by our Japanese colleagues. So, okay, let's look at the neutrophil lymphocyte ratio from these guys. Mr. O had the highest that I've ever seen. Remember now, control was 2.1. His was 98 in the first, actually 6 or 8 hours. In fact, his lymphocytes were just bottoming out dramatically. Mr. S had 32 and Mr. Y had 6.7. And in the dose reconstructions, Mr. O's estimated dose is somewhere between 16 and 20 gray, Mr. S somewhere between 6 and 10 gray, and Mr. Y 1 to 4.5. Mr. Y survived, but you can see the neutrophil lymphocyte ratio taken in the first 6 hours here would certainly point you highly toward a suspicious circumstance. Here's some references for Tokumura. There's a lot been written on it, including cytogenetic dosimetry, so you can check some of this out. All right, let's look at the receiver operating curve analysis, ROC analysis. So here we're going to look at sensitivity and specificity. We're going to look at our neutrophil lymphocyte ratio as a medical test. And so we're going to consider Bayesian statistics, Bayesian probabilities. So mu is the probability that Y happens given that X has happened. Okay, so the probability that something happens given that you've had 2 gray or more, it's probability of Y given at X, so it's a conditional. So the sensitivity of a test is defined in our situation here using 2 gray as our threshold, the fraction of those with dose over and 2 gray who are positive for the test. So this means the probability that if you have a dose, D plus, then your test is going to be positive. Or if you have a dose, your neutrophil lymphocyte test is going to be positive. Okay, that's important. The specificity is the fraction of those without dose who have a negative test. So the probability given no dose or minimal dose, your test is negative. So those are both important. We want to have as high sensitivity and specificity as we can get. So the sensitivity is also defined as the true positive over all positives. So it'd be true positive and false negatives. The specificity is defined as the true negatives over all negatives, true negatives and false positives. Those are the definitions. So really, though, what we want to look at is what's called the positive predictive value and the negative predictive value. And so the positive predictive value is the probability that given the test is positive, then we say that patient has probably had a dose over 2 gray. So if our neutrophil lymphocyte ratio is over our threshold, then we say there might be 2 gray or more. And really, we want to send them then to more definitive testing. And conversely, the negative predictive value is if the test is negative, if our neutrophil lymphocyte ratio is under controls, then you probably don't have a dose of 2 gray or less. So the probability the dose is less than 2 gray. So these are actually BARDA definitions, and we could make it 1 gray, but we could, make it whatever. The positive predictive value and the negative predictive value are dependent upon the prevalence of irradiated patients in your population, which you're not going to really know in a weapons event, but you can make some assumptions. So what we want to do is to look at the neutrophil lymphocyte ratio and look at the diagnostic performance. So we want to be able to discriminate cases greater than 2 gray from normals. And so the ROC curves are used to show the trade-off between sensitivity and specificity for every cutoff. So if you increase your sensitivity, you decrease your specificity. So there's a trade-off between these two. I mean, you want to get them both as high as possible, but you increase one, you decrease the other typically. And so one statistic that's used is the area under the ROC curve. I'll show you that. So our question here then is on the ROC analysis, we want to determine a threshold value for the neutrophil lymphocyte ratio such if our neutrophil lymphocyte ratio is over that, we're suspicious and refer the patient for more definitive health physics and medical testing. So what I did in this analysis was minimize what's called the Yoden-J statistic. It's actually just the sum of the sensitivity and specificity minus 1. The maximum value of sensitivity is 1, the maximum value of specificity is 1. So this statistic is the sensitivity plus the specificity, minimizing the sum. You could actually do it differently. You could maximize sensitivity, or you could look at specificity. So it's just one way to do it. So here is the statistical software I use. It's called MedCal. Almost all, as far as I can tell, almost all of the major statistical programs have ROC analysis, at least the ones I've used. But MedCal I like. I'm not trying to give a commercial for it. It's out of the Netherlands, and I bought it, 8 or 10 years ago, and they just keep updating it. Every time I come on, they say there's an update with no cost. So it's real good. So this is what I use for the ROC analysis. And so basically the way this works, you have a file and you define whether this neutrophil lymphocyte ratio is either a control or a positive. So we had 33 positives and 125 negatives here. And so we go and we look at the threshold, and then we calculate sensitivity and specificity for that given threshold. And so we want this to hug the left-hand corner, upper left-hand corner as much as possible on the area under a curve. So the area under this curve is 0.865 here. It's not bad. I wish it were a little higher. We have a line here, the 50% curve. If you have 50% probability, this is like you flip a coin. So we want it to hug that upper left-hand corner as much as possible. So in the analysis here, in looking at maximizing the Yoden-J statistic, we said the criterion was 3.3. So if the neutrophil lymphocyte ratio is over 3.3, then we'd be worried. The sensitivity here is 66.67%. Specificity is 96%. And so it has good specificity. So if the test is negative, you probably don't have a significant, I wish it were a little bit more sensitive. You can actually improve the sensitivity a little bit by adding other parameters. And we've done that, and I think others have done. I believe Dr. Blakely's done that also, but just in a multi-parameter test. But this is just looking at the single parameter here. So here is the data that you get out, and I maximized this at 3.3. But you know, we could maximize our sensitivity. We could go up to 2.75 or whatever, or 0.75 or whatever. We could maximize sensitivity and specificity. But here I just looked at the combination. That's just a very traditional way to do it. But you get all out of the program, you get all of these different values. So let me show you then what we're actually dealing with. So on the right hand, on y-axis, we have neutrophil lymphocyte ratio. X-axis, I have whether it's a control or an irradiated person. So 0 is our control. And here I've got a criterion line of 2.7, just for example. So with controls, most of them are under the line, but there are some that are above the line. So we would call these positives, but since we know they're controls, they'd be false positives. Looking over at the irradiated group, most of these are above the line appropriately. They should be above. We know they're irradiated, but you've got some that didn't respond well. And I think it's maybe 5%, no more than 10%. And so these would be false negatives. So I actually thought about drawing curves, but what you see here is that the control curve and the irradiated curve, they overlap. And this is true for most things in medicine. So with this criterion, the sensitivity is 75.8%, the specificity is 86. So I decreased my specificity by increasing sensitivity. So I'm going to finish up here very quickly. So for this data set, and when we published it, we said the decision point is going to be 3.33 for optimizing or maximizing the sum of sensitivity and specificity. Area under the curve is 0.86, sensitivity of 67%, specificity of 97%. So this is similar to maybe some of the medical tests we do, like a PSA or some of these tests. The positive predictive value was good, though, 85%. A negative predictive value was 92%. This is using the number of cases that I had in here. Of course, in a real accident, you're not going to know your prevalence, but you can make some assumptions here. So the bottom line is, when we have a known criticality accident or a nuclear weapon event, we know it's happened. We're triaging people. We get a neutrophil lymphocyte ratio. If it's greater than 3.3, then we ought to be suspicious and refer them to further evaluation, health physics and medical. So that's our bottom line. And in conclusion, this is only a screening test. And so, you know, if we know the radiation event has occurred, this could be gamma also. If we know it's occurred and this neutrophil lymphocyte ratio is greater than our threshold, then we should be cautious and refer the patient for more sophisticated analysis. So test appears to be valid after about 4 hours. It takes a little bit of time for these cells to do their thing, but the test appears to stay positive for 10 to 15 days. So that's our bottom line here. Now, when you have a scientific analysis, it's always, you know, it's always the thing to show your colleagues. So let me show you our colleagues here. Actually, I have my son on the call with us here. These are his dogs, Piper and Phoebe. Piper would be the chief scientist, I think, in this cohort. She is the clearly the leader of the pack here. Rex and Xena are my youngest son's dogs. So this is my scientific team here in East Tennessee. You know, in East Tennessee, we love our dogs. And I'll just finish up a photo that Dr. Iddens did of Tennessee in the fall. So I'm going to stop and share this and be glad to take any questions or anything you might have. So thank you.
Thank you, Dr. Goans. So I see we have a hand from Paige Witter.
Okay.
Hi, thank you. This is really interesting. I have two very general questions. One is, are there other illnesses that could impact this neutron to lymphocyte ratio? You said that it's a non-specific marker for inflammation. So if someone is sick prior to irradiation, how, like, is that something that those ratios would be impacted?
Yes, yes. That's true. And in a population, you're not going to know until you actually do a medical history. You're not going to know who is sick.
Okay.
So if somebody has the flu or they have a cold, that could be elevated. And as I noted, neutrophil lymphocyte ratio is elevated in many different states and cancers and all sorts of immunological things. So, you know,
so the ratio could be elevated enough to be in this same discrimination level. Okay.
It could. But then another thing you could do is see, you know, okay, we've had the prototypical scenario is 10 kilotons, a detonation in Washington, D.C., Lafayette Park, you know. And I just came back from Atlanta. We had a seminar there to see what data we would want to do if a weapon went off in Atlanta. I mean, it could happen in any major city. And so one thing, okay, so if I have a patient that comes in, I do the blood count, it's elevated, then I start asking some questions, you know, are you sick? Do you have any medical problems I should know about? And also, where were you relative to the blast? If someone comes in, they're 10 miles away from a 10 kiloton weapon, obviously their dose is going to be very minimal. So there are other ancillary data that you can get in with this. So it's just a screening test, and that's kind of what we're doing.
Very cool. Thank you. I had one more question coming from a DOE space and a non-medical field. Are these kinds of machines that can do a CBC with diff, are those pretty standard in a typical medical office already?
Yes, most medical offices don't do their own CBC. I had a medical office. I used to do my own CBCs. But yes, I mean, these are easily available. They're portable. Most doctors send the things to a major reference lab, but yes, they're available.
Gotcha.
You can buy them. Yeah, sure.
Cool. Thank you.
Dr. Blakely.
Hello, Ron.
Hey, Bill, how you doing?
So good to see you.
See you.
I want to compliment you on such an excellent seminar. I always have enjoyed the way you give your lectures because of integrating it into really cases. I always learn from your talk. My only thought into complimenting your talk is to point out that several years ago, as part of a NATO exercise, I worked with the AFRI MRAT team, and we were sent data from 100 cases that came out of the Metropol database, along with 6 other NATO groups. And as working as a function of the AFRI team, MRAT team, one of the things that my colleague, Dr. Bolduc, and I did is use the initial neutrophil lymphocyte ratio, which we learned from you, as our initial cut. And so we gave an initial report back within minutes of receiving the data from 100 cases using solely the trigger that you just mentioned. I can't remember exactly the threshold value I had, but in subsequent analysis, we caught every case of HARS that was 3 or 4. That is, every life-threatening exposure was caught by that initial screen of the neutrophil lymphocyte ratio, endorsing what you're saying. And this was data from real cases of radiation accident patients, which were, so, you know, I'm a believer of this tool for this purpose. And in this one case, you know, those are the people that would be either put into a transplant queue or for giving initial one of the 4 approved drugs. If I could just make a comment from the previous individual, There are at least 4 companies that are moving through FDA and are deploying handheld blood cell counters that do neutrophil counts. They all do 5-point differentials that would include lymphocyte neutrophil counts on a handheld point of care within a minute or 2 analysis, battery operated type of unit. Again, compliment you. I keep on learning more and more every time I listen to you. Great seminar. Go ahead.
Thank you. Yeah, Bill and I go back to the mid-1990s together, talking about this and his BAT program and subsequent editions of that. Yeah, so it's good to see you again.
Thank you. Do we have anybody else? So Dr. Jeff Chapman?
Sure, thank you. I just want to add to what Bill said, Dr. Goans, that fabulous presentation, really enjoyed it. Question about the endpoint there, the measurement in absorbed dose, Gray. That is there any kind of dependence on the neutron to photon ratio?
Yeah, I'm sure there would be. And of course, we're not going to know that initially in the triage. And in these cases, some of them were liquid, like Y12, some of them were solid criticality events. And so, the neutron flux distribution is different in all of these, and the neutron photon ratio is going to be different. So, I don't know that we have the sensitivity to discriminate this. This is just meant to be an initial triage test. But yeah, it's going to be, and we're not going to know that, at least in the near term.
Is there any work being done to make that evaluation, to study that?
Well, we could probably go back. We've got these 13 cases. We could probably go back and look at the ratio and look at the neutron gamma ratios. And Bill, you had a comment here.
Oh, that's a very, very good question. I published a data set from baboons, which is a beautiful data set involving 6 to 8 animals at 1 gray increments, going from 1 out to 6 or 7 gray, with both neutrons and photons. It's the only data that exists in the world, I believe, that's using large primates. We've published that, and at least for that quality of the neutron gamma radiation, we would be actually able to analyze that. The paper that we published pointed out that the hematology profiles are different for photons and neutrons. So you have to have neutron data to predict responses consistent with what Dr. Goans has just said, to predict whether it be lymphocyte depletion or neutrophil lymphocyte ratio. You have to do the study with the quality of radiation, because the neutron pattern is different than the photon pattern.
Yeah, and we do have data for gamma accidents. It's just I had better data for criticality, just to be honest with you, and that's what we published. But we had a famous accident here happened in Oak Ridge in 1971 with cobalt-60, and the whole body dose was about 3.5 gray, and the patient had hematopoietic HARS, and the neutral lymphocyte ratio was out of whack there also. So this actually works for pure gammas also, which we see more of. We don't really see criticality very much, thankfully. Yeah.
Great discussion. Was there anyone else? Rebecca.
Or Barkowitz. I was, I guess, thinking, kind of what y'all just thinking. I'm in a hospital facility at UT Southwestern in Dallas. So just, I guess more likely today, right, is if a dirty bomb accident or something. So if someone had acute exposure from that type of radiation incident, I guess what you just said, Dr. Goans, is that the ratio, we could still use the screening test.
That's my, yes. So,
Thank you.
All right, well, I don't see any additional hands or anyone in the chat. Bill, is that you waving your hand, or with the?
I was, Dr. Goins, with the dirty bomb, are you going to get significant dose exposures to see changes in neutrophil lymphocyte ratio with a dirty bomb?
no.
I agree.
You know, when I teach my health physics class, I use hotspot, the Livermore program to simulate a dirty bomb, like, cesium-137 on, 75 pounds of TNT or whatever. And what you find, all of this is you get tremendous surface contamination, but you don't get much personnel dose. And so, if you're real close to it, you may have trauma from flying debris or something, but the actual dose from an explosion like that's minimal, generally speaking.
Okay, well, that was a great discussion. Again, this will be, we're going to end the recording here.